Okay, we're going to start on section 20.6 RL circuits. And because section 20.7 energy stored in a magnetic field is a very short one slide discussion, we'll continue on with 20.7. So this covers both 20.6 RL circuits and 20.7 energy stored in a magnetic field. Let's start with the PowerPoint. I need to bring this up to date. Okay, a circuit element that has a large inductance, for example, a closely wrapped coil of many turns, is called an inductor. The circuit symbol for an inductor L is as shown in the bottom figure. We will always assume the self-inductance of the remainder of the circuit is negligible compared with that of the inductor in the circuit. Let's see if we can gain some insight into the effect an inductor has on a circuit. Take a look at the two circuits here. The top figure shows a resistor connected to the terminals of a battery. For this circuit, Kirchhoff's loop rule is shown here. E minus IR equals 0. The voltage drop across the resistor is IR. Okay. In this case, we interpret resistance as a measure of the opposition to the current. Now, let's consider the bottom circuit, which consists of an inductor connected to the terminals of a battery. At the instant the switch in this circuit is closed, because IR equals 0, the EMF of the battery equals the back EMF generated in the coil. So we have this relationship. E equals minus L delta I delta T. From this expression, we can interpret L as a measure of opposition to the rate of change of current. Okay, the top figure, I don't know that it's a top figure. Well, it is the top right figure shows a circuit consisting of a resistor, an inductor, and a battery. Let's suppose the switch is closed at T equals 0. The current begins to increase, but as you know, the inductor produces an EMF that opposes the increasing current. As a result, the current can't change from 0 to its maximum value instantaneously. Our equation shows that the induced EMF is a maximum when the current is changing most rapidly, which occurs when the switch is first closed. As the current approaches its steady state value, the back EMF of the coil falls off because the current is changing more slowly. Finally, when the current reaches its steady state value, the rate of change is 0 and the back EMF is also 0. The lower figure plots current in the circuit as a function of time. You might notice that this plot is similar to that of the charge on a capacitor as a function of time. In that case, we found it convenient to introduce a quantity called the time constant of the circuit, which told us something about the time required for the capacitor to approach its steady state charge. In the same way, time constants are defined for circuits containing resistors and inductors. The time constant for an RL circuit is the time required for the current in the circuit to reach 63.2% of its final value, and is given by this equation. Tau is equal to L divided by R. The current in the circuit shown here is given by this equation. I is equal to E over R times 1 minus E to the minus T over tau. That should look familiar. It's very similar to the one that we had for RC circuits. This equation is consistent with our intuition. When the switch is closed at T equals 0, the current is initially 0, rising with time to some maximum value. Now, this is actually section 20.7, energy stored in magnetic fields. The EMF induced by an inductor prevents a battery from establishing an instantaneous current in a circuit. The battery has to do work to produce a current. We can think of this needed work as energy stored in the inductor in its magnetic field. The energy stored by an inductor is given by the equation shown here. PE of the inductor is equal to 1/2 Li squared. Notice that the result is similar in form to the expression for the energy stored in a charged capacitor, which is PE potential energy equals 1/2 C delta V squared. And that is the end of this chapter. And I will end.